Okay, so the last point I wanted to make is that on the exams, try to have as much things worked on this first paper as possible. Give a lot of math when I was grading. So if your final answer is wrong, if I'm able to see track some understanding in your worksheet, in your scratch paper, I'm able to give you some credit, right? But if I can't see anything there, then there's no way to get credit. So try to write as much as possible on that scratch paper. So we're going to get started with the class. We've lost some time already. But I'll be giving more detailed information by next class, about how the details of what to expect on the finals, okay? All right, any concerns or question before we get started? No, I know that. Okay, so we are going to ANOVA today, and an ANOVA is simply analysis of variance, right? And we'll try to cover this objective. It's quite a long list, but just as we did in regression, we're not going to be going into details of these items, right? Analysis of variance is under another subject, another course called design of experiments. Design of experiment is a 1 semester course, right? So we can definitely do 1 semester in 1 class. So what I'm going to do is to remain on the surface, but I'll give you enough information that if you are to conduct a research today using ANOVA, you have the basic thing you need. And simple, little more Google search will give you every other remaining item. But I'll give you enough framework that will enable you conduct analysis of variance test. Okay. And so I wanted to run down this very quickly. So this is like an overview of all the tests we've covered in the class, right? So the first one is a t-test. You remember you have paired and dependent t-test. And the point is that the t-test is used when you are comparing 2 groups. Right, so if your focus is to compare 2 groups or 2 populations, t-test is your best bet, right? It's the most efficient test to do at that time. But if you have, and I'm going to jump to ANOVA, the third one, if you have more than 2 groups, then you need an ANOVA. Okay. Okay, so what happens here is, say, for example, I want to compare performance of 2 classes. I can use t-test to do that, A and B, class 1 and class 2, or whatever I call them. But if I want to compare 3 classes, 4 classes, 5 classes, the only way I can do it with a t-test is that I pick those classes in pairs, right? Let's say I have 4 classes at class 1, 2, 3, 4. I pick class 1 and 2, compare them using a t-test, find out the class that is better, then pick class 3 and 4, compare them using a t-test, find out the one that is better, then pick the better of the 2 and compare those. I'm now able to that. So I'm conducting 3 tests just to do that for comparisons. But with ANOVA, you can do that comparison all at once. You can compare the 4 tests all at once, or 5, or whatever number of tests. And so when you compare tests in pairs that way many times, the error, the chances of getting the wrong answer increases. So the type 1 error, it gets inflated, right? Because each test you conduct, you have your significant level to be 0.05, right? And if you have 4 tests, then you virtually don't have 0.05% error anymore. It could go as far up as, it's not exactly 20, it's not exactly 20, it's not exactly like 5 plus 5 plus 5, that would be 20. It might be around 19. There is a factor for calculating that. But the chances of making mistake would inflate so much, right? ANOVA avoids that by doing only 1 test instead of those multiple t-tests, right? So what we do is that whenever you have 2 groups to compare, t-test is your best bet. If you have more than 2 groups to compare, ANOVA is the best bet. But if you use ANOVA to do 2 groups, it will just narrow down to t-test. The result will be exactly as the result you get if you do a t-test, right? So ANOVA is just kind of more global, but it's more efficient when you have more than 2 tests, okay? So that is the advantage of t-test over this. So some of this thing I'm explaining now, I hope you're picking them up. You have first part of your homework on this section, trying to check or test for this knowledge, for what I'm explaining now. And it might also be part of your written exam. So I hope you're paying attention. Then you have regression. We skip that. Regression is used for prediction. Okay, so if you're not trying to compare groups, you are trying to use some information you have to predict an outcome, then regression becomes your tool, right? So in this class, we only did simple regression, which means we used only one variable to predict an outcome. In real life scenario, as we explained last class, that doesn't happen. I mean, most things in life are so complex that you can't explain them with just one variable. So what you normally do in real life is a multiple regression, not just simple regression. So you do multiple regression. And in that multiple regression, you can actually have quadratic variables included, so variables that we talked about last class, we talked about like sports, where people at young age will be, doing well, and at a certain age, if they continue, their performance is going to begin to drop, right? So you can have variables like that included in certain regression, but not in the type we did last class. We just did the basic one, which is a linear straight line regression, okay? So when you want to make prediction, regression is your tool. But when you're comparing groups and they are just two items, two groups, you are using a t-test. T-test is the best for that. If you are going to compare more than two groups, then ANOVA becomes your best tool, okay? Any question or concern about this? And of course, the advantage of ANOVA over t-test we mentioned is that ANOVA is able to keep the error rate the same, right? T-test will inflate the error rate. If you have many multiple groups and you want to do many t-tests to answer the question, then the error rate will just go out of control. All right, so that is that about this slide. Let's move on quickly. We have a lot to cover. So how do you state the hypothesis for analysis of variance? Okay, so remember in t-test, and let me use another color to do that. Remember in t-test, we usually do H0, or the null hypothesis is comparing mu1 with mu2. Because you just have two items. But in ANOVA, we are saying that, let me use red for that. In ANOVA, we are interested in comparing more than two groups. So because of that, it's normally, the hypothesis is normally written in words, because let's say I have 10 groups to compare, then my H0 will actually be written as mu1 is equal to mu2 is equal to mu3, right? All the way to being equal to mu 10, okay? But the complication why this is simple enough, the problem with ANOVA in symbol is when you want to write the alternative. The alternative hypothesis, and maybe we state it in word and we'll come back to why this is difficult. So let me write it in words here. So ANOVA hypothesis says H0 is all group mean are equal. That's what ANOVA is saying, that all the groups are equal. That is the null hypothesis. The alternative hypothesis is that at least a pair of the groups differ. Right? What does that mean in this context? So it's saying if I have 10 groups, for example, the alternative is saying, alternative is not concerned that all of them are not equal. It's concerned that at least 2 groups out of that 10 group are not equal. And once 2 out of the 10 are not equal, that is, it means the null hypothesis is rejected. The null is that all of them are equal. So all you need for the null to be rejected is for only one group to be different from all the other 10. right? If you try to write that in number this way, you're going to be doing mu1 is not equal to mu2, and mu2 is not equal to mu3. And you can imagine that. You continue doing this until you get to 10, and then you have to come back anyway, because you still have to compare. I just compared 1 and 2 and 2 and 3. You have to come back to compare 1 and 2 and 1 and 3. You know, so it's going to be a chain of all stuff. So to make that simple, we usually avoid writing the hypothesis statement with symbol. Not that it's impossible. A simpler, more efficient way is to write it in words the way we have it here. So again, so for ANOVA, the hypothesis, the null hypothesis is that all group means are equal, all of them. And the alternative is that at least a pair of the group mean differ from every other one. Okay, so take note of that and note the difference between this and the hypothesis for t-test. The t-test hypothesis says the two groups are equal. That is the null hypothesis. And the alternative hypothesis simply says the two groups are not equal, right? So you can see that it is very easy to state, and that is why symbol works for t-test. But for ANOVA, writing it in words will be a better way to go forward. Okay, so one other thing to take note of is that in ANOVA, the dependent variable, let me use red, the dependent variable must be continuous, right? It must be continuous. Continuous means it must be a data that you measured. It cannot be a category, it cannot be numbers that you count, okay? Why the independent variable must be categorical? It must be discrete and categorical, if you remember chapter 1, right? And categorical means it had to be a count, and it's normally a count of groups, right? So the independent variable is the variable that contains the groups you want to compare to each other. The dependent variable will be the variable that contains the information you are trying to check whether it differs among the, right? So if it will be a class assessment and I'm trying to compare 3 classes, class A, B, C, and D will form the variable for independent, will be the independent variable. Why exam scores will be the dependent variable. Okay, so this condition must be met before ANOVA could work, right? So when you're going to conduct a test and you think through this thing and it doesn't appear to be what you have, then you can actually use ANOVA. Okay, all right. Any question on that? Okay, so let's move on. I think I need to stop this to be able to advance this slide. Okay, and we have this also happening. So let's try to clear this. I know we had this problem last class. Let's hope it clears. Okay, it clears. So we go on to the next slide. Okay, so here is an example of what the ANOVA is. And I think at this point, we should stop and go ahead and get you to run SPSS, to run the data, generate the information we need, and then we come back here and discuss the outputs. Okay, just the way we did last class. Okay, so over here, the design of this unit is just similar to last class. So I've done a video here that will enable you import this data set here, the diabetes data set. The video will give you a guide on how to import that into SPS, not really how to import that. I believe you know that by now. But the video will give you a guide on how to conduct ANOVA, analysis of variance tests, using the data set, okay? And when you do that, copy and paste your output in a Word document. Or you can leave it on your screen since we're already here and we're working in the lab here. You can leave it on your screen. So we're going to look at those outputs and try to explain them just as we did in last class, okay? So please go ahead and do that. Let's hope we can do that in 10 minutes so we'll have enough time to discuss the output itself. I still have the earpiece here, so if you need one, let me know. If you still have challenge, I know at least one of you here wasn't here when we were working on all this. So if you still have challenge importing data or doing those preliminary things, also let me know so we can get it in. But let's hope we work very quickly and have the output ready, and we'll have time to do interpretation. I'll give you just maybe 1 or 2 more minutes, and then we regroup to discuss the outputs. Okay, so we are gonna go ahead and work together here. If you're not done, you can follow the video later on and complete that. And you'll be repeating everything we've done today on an exercise, just like yesterday. So that will also give you additional practice, okay? And as mentioned before, if you encounter problem on doing this, maybe a picture of where that problem happened would be helpful, right? And I just noticed, and we noticed there are version differences. So the computer I used to explain in the video might have the latest version. And so some other things might be slightly different from what you have, but whatever that is in the video, you will find it in the old one. It might be rearranged, a little bit. So if you encounter any problem when you're working on this, just take a picture of the page where you are and let me know, and I'll be able to trace what the problem is, okay? All right. Of course, that excludes technical problem with installation. I'm not able to do that. IT will be the one to help you. Okay, so let's get back here. Let me turn this on back. Trying to integrate the laptop with the. Okay, so one of the outputs, you'll get this one. Did you all get this one? At least that will be an indication that most other ones will be correct. Anybody got a descriptive statistic that is different from the one we have on the screen right now? No? So we all got the same thing. Okay. So that's an indication that every other thing we did should be in order. Okay. So so when you are doing this, you check the box that said descriptive statistic. The descriptive statistics gives you these basic values. Remember, what we are doing is analysis of variance, right? Even though that is the name, what the procedure is actually doing is comparing means, trying to know. You remember our alternative hypothesis. We were trying to compare. Okay, that all went off. We're trying to compare the mean, right? That is the null hypothesis, comparing the mean. And the alternative hypothesis is that one of the mean is different. So what the procedure is going to be doing when you execute it is to compare all these mean here, right? And ask the question, is any one of them different from at least one other one? That is what it's trying to do, okay? And so these are descriptive. They give you an initial idea of what your distribution or your variable are. They are like, but you're not able to answer the question here, okay? So we know that 123 is quite different from 110, at least, right? But we don't know that the difference is statistically significant, and that is the problem, right? So ANOVA will be conducting a test to tell you whether it's statistically significant. And this is the kind of test we did in t-test with hand. It's the same thing ANOVA is doing, but it's doing it for more than 2 groups. Okay. So let's go ahead. And the next thing we want to do anyway is that for this comparison to be fair, ANOVA needs that the variances of each group should be about the same thing, right? And it makes sense that if, for example, you want to compare height with weight, for example, weight is in kilogram and it runs, around 100, above 100. I mean, in pounds in this context, it runs above 100, right? But let's say you measure height in feet, the highest you could get is 7. Now, if you have a data that spreads from 1, maybe not even 1, actually maybe from, let's say, 3 or 4 or 2, from 2 all the way to 7, that is the width, the spread of that data. And then you're comparing it with weight, which could spread from, maybe 60 or thereabout all the way to maybe 200 and something, right? So you see, the variances are not equal. So it's not proper to compare these two. When you take a class in ANOVA in design of experiment, then you are told what to do. You learn what to do to adjust, those weights, to make them comparable. Okay. But the key thing I'm explaining here is that one of the assumptions that your result in ANOVA is correct, the output you will get, because whatever you give SPSS, it runs through it as a machine and gives you a result. It doesn't care. So these are the logic you as a human being will be doing. So what you want to do is to make sure that the variances and the spread of your data set are about the same. That will be comparing apple to apple. Otherwise, you're comparing apple to orange or something else, right? Okay, so the first thing you do is to conduct the test of homogeneity of variance. This is another way of saying a test of, where's my pen? This is another way of saying a test of equality of variance. Right? Homogeneity is just the same thing as equality. It's a fancy word for that. So this test is trying to check whether the variances are equal, right? And the person who invented it is Levin. And so we call this Levin's test. So some people will say Levin's test of equality of variance. Some people will say Levin's test of homogeneity of variance. So if you find this in the concept questions and maybe somewhere in the assessment as well in the homework, so when you are being asked about homogeneity of variance, equality of variance, Levin's test, technically you are being asked the same thing. Okay, so we can refer to it by the developer's name Levin, or we can refer to it in the normal, ordinary term as equality of variance, and then in statistical term, people will say homogeneity of variance. Okay, I hope that is clear now. So how do you conduct that test? The test is here. First, let us write the hypothesis for this test. The test has the null hypothesis that says all groups have equal variance. Or equal variances. That is what the null hypothesis for this test, for Levin's test, that's what the null hypothesis says, or the null hypothesis for homogeneity of variance test, or the null hypothesis for equality of variance test. So it can go by any of these names. So that test is saying the null hypothesis that all the groups have equal variances. The alternative hypothesis is that at least one group variance differs, right? So if only one group has a variance or a spread that is different from other one, Levin's test will fail, okay? But if all the groups have just about the same variances, Levin's test will pass. And if you meet the Levin's test, which is something as the test of equality of variance, which is something as the test of homogeneity of variance, if that test is met, then your result carries through. If the test is not met, your result is not going to be correct. But there is a correction for that. And that correction was built into SPSS. And we're going to look at that correction as we go down, okay? So for now, how do we know whether the result is met, the test is met or not? You look at the p-value, as always, right? You look at the p-value. And remember, when the alpha value is not given to you, by default, it's taken to be 0.05. So you see that as we are executing this thing, SPSS is automatically assuming 0.05, except you change it, okay? So if we look at the p-value, and this is an addition for the new version of SPSS, right? So your own output might not have that. What I mean is this section. Your own output might not have that, right? But it will definitely have the first one, the first line, okay? So the first line is what we're interested in. It is comparing the mean. Okay, so it's testing the homogeneity of variance based on the mean. Remember the formula for calculating variance? There is a mean somewhere there. So this test is conducting equality of variance based on using that mean. You can see the value other ones are using. Some are using median, some are using some other adjustments, but we're focused on the first one. So what we do is to look at the p-value, right? And remember in SPSS, p-value is something as your significance level. So it's Sig, that is your p-value. So the p-value here is greater than 0.05, right? But remember what we do when p-value is greater than 0.05, it's greater than alpha. So you see that p-value here is bigger than alpha. So whenever p-value is bigger than alpha, you fail to reject the null. Right? So because p-value is bigger than alpha, we fail to reject the null. You know what that implies? It implies that the variances are equal, because the null is the one that says the variances are equal. The alternative says the variances are not equal. So if you fail to reject the null, it implies that the variances are equal. And if the variances are equal, then the assumption is met. Right? So the assumption means, I mean, the assumption, the condition for the result to be correct is met, so you can go ahead and interpret the result. If this p-value were to be less than 0.05, it means we reject the null hypothesis. And if we reject the null hypothesis, it means we are supporting the alternative, which says that at least one group don't have equal variance with others. And if that is the case, then you cannot interpret the natural result that comes out, the ANOVA table. We have alternative result that you will report for a correction, okay? All right, any question at this time? Okay, so what I've done in the homework and in the concept question, I've built in all this and I'm highlighting, so you'll be asked questions as reminders to be able to recall and remember or present them, okay? All right, so let's move on to the next slide. Okay, this carried through, so we're gonna try to clear it. It's on video, so you have it back. Okay, so let's clear all that and move on to the next slide. All right, so if the homogeneity of variance test is met, right? If the variances are equal, the table you interpret is the ANOVA table. That's what gives you your result for the analysis of variance. But if this test is failed, right? If this condition is not met, that is, if your p-value is less than 0.05, it means that one of the group has a variance that is different from every other group. Then the result, you will not interpret this result, the ANOVA table. The result you interpret will be the robust test for equality of means. Okay, and I should have placed it just behind that. I think that might be better. Arrangement. Okay. Keep this. Let's just put this behind that. Where is it? Yeah, so let me put this up close so we can talk about them side by side. I think that will be better. Okay, so I will repeat that again, right? If the analysis of variance test is met, if the variances are equal, which means the p-value was bigger than 0.05, which implies we did not reject the null hypothesis. If the variances are equal, then this is the table you interpret for the result, which is ANOVA table. But if the variances are not equal, if the p-value here is less than 0.05, which means we reject the null hypothesis, which means we are saying one of the variances is bigger than other ones, then the table you interpret is this one, test of equality of means. Okay, so these are the kind of things I'll be checking for in your assessment to know whether you know which table to interpret. So once we conduct this test, that's why you must do the test first. Once you have the test done, and you know which table to interpret, you go ahead and interpret the table. And these tables are telling us, in general, and we're going to write the null hypothesis again. This table here, the ANOVA table and the robust test of equality of means table is simply testing the null hypothesis that all, okay, this started again. All group mean are equal. That is the null hypothesis. And remember the alternative hypothesis, where we wrote it also in words, right? The alternative hypothesis is that at least one group mean differ. Okay. At least one of them differ, right? Okay, so that is what this table is testing, and that is what the next table, robust test of equality of mean, that is also what it is testing, right? Okay, so let's go ahead and see how this is interpreted. Just as always, you focus on the significant value first, right? If the significant value is greater than 0.05, you fail to reject the null hypothesis. If the significant value is less than 0.05, you reject the null hypothesis, right? Okay, so now it is less than 0.05, which means we are going to reject the null hypothesis. So we could say we reject the null hypothesis. Or you can just write H naught, right? We reject the null hypothesis. Okay, and so once you reject the null hypothesis, oh, sorry. Yeah, once you reject the null hypothesis because the p-value is less than 0.05, then you're going to conclude in support of the alternative. So we know that at least, but let's put it more properly. So we reject the null hypothesis and conclude okay. We reject the null hypothesis and conclude that at least one of the group means differ. I'm going to change all these tools by next semester. They're getting weak. So at least one of them differ. That is the conclusion of this test. Okay. So remember what we're trying to do. We're trying to compare glucose level of women who have had different number of pregnancies. So some had 0, 1, 2, 3, or 4 pregnancies. So we're trying to compare their glucose level, right? So what this result is saying is that at least one of the groups has a glucose level that is different from every other group. Okay, that's what it's saying. So you want to write the statement in the context of the problem, right? So this is a general template, you know. So I should be saying at least one of the group of women have glucose level that differs from every other one, right? And maybe I should write it down here in green. So you want to make sure that when you're reporting your results, you're reporting it in context of the problem you're solving. Okay. So we could say that at least one of the groups of women has glucose level that is different, that differs from other groups. We can say from other groups mean. Okay. One of the has mean, let me put the word mean here. So remember again that what we are comparing is mean. We're not comparing the individual participants to themselves. We are comparing the mean of each group to the other one. So you want that in that direction. So one of the groups of women has mean glucose level that differs from other group means, okay? But so this answers that question. You know that at least for a fact, but you don't know which group that is. This test does not give you that information, right? And that is what the next set of tests will give us. But remember, we were saying you can only conduct this test, use this ANOVA table right now to report your results when the assumption of homogeneity of variance is met. And so, by the way, I was almost missing an important information. After you've stated your conclusion in words, you have to provide evidence in numbers, right? Because somebody is reading your report, you're not going to put this table directly this way on the report. It might be on the appendix. So the evidence is provided this way. Let me write it back on red. Let's continue with green. So at the end of all this, you open a parenthesis and have F. So the test statistics we are using here, you know, is T on when we are doing t-test. Here it is F, right? So F test here, parenthesis open. You have your degree of freedom 1, that will be this one. And you have your degree of freedom 2, that will be this. It is the two added together that gives you the total here, okay? So focus on degree of freedom 1, degree of freedom 2. Then the other element you want to pick is your F, and the last element you want to pick in your evidence is your the p-value. So you're going to write this like this, and let me try to move all this so I can have them in proper format. I think not done the selection here before, but let's see. I hope it works. Okay, that was not very successful, but I think it could solve the problem I want. So let's try that again. Okay, bear with me. Okay, so when you're done with all that, you ought to put in parentheses your evidence. And this is the way to write that evidence. Parenthesis open. Right, your F statistics, parenthesis open, degree of freedom 1, which is 3, degree of freedom 2, which is 420, parenthesis close, is equal to your F statistics, which in this case is 4.784, right? After you've written that, then you have semicolon, you write your p-value. P-value is equal to 0.003, right? Then parenthesis close. Okay, so this is your numerical evidence supporting your statement in words. So with this evidence, people can easily tell what your result was like. I can see the sample size. I can tell the number of groups you compared from degree of freedom 1. I can tell there are 4 groups because degree of freedom is n-1, remember? So I can tell there are 4 groups that you compared. Then I can look at your within groups, DF, degree of freedom 2, I can tell the total sample size that you use to do the data analysis. So that's why these things are reported in the results as evidence. So from this, without seeing your data and seeing your table, I can tell the number of groups you compared, I can tell the sample size you use, and I can tell the statistics, the test statistics results, which is your F statistic, which is here, right? And I know that this is quite big, that it should be significant. But to confirm that, I can look at the p-value and tell that your result was significant. And if the result is significant, this result of this ANOVA table test, it simply tells us that one of the group has a mean different from every other one. It doesn't tell us which one. So we're going to dig further to find out which group has a mean different from the other one. So if you state your result in words and you don't include this evidence in parentheses, which is in numbers here, your result statement is not complete, because this is evidence supporting what you've said in words. Okay, so be sure to include that to have full mark on that. Okay, any question? Okay, so the way we interpret this is the way we interpret the outcome from the next slide, right? And let me clear this here. Okay, so remember we said if the Levin's test is not met, if the result of the Levin's test tells us that the variances are not equal, right? Yeah, that the variances are not equal, then we can't interpret this table we just interpreted right now. We can't interpret the table on the previous slide. If the variances are not equal, then we can't use this table to report our result. If the variances are not equal, this is the table you will use to report the same result. And the result you have is just exactly the same way we reported it in the previous table. Exactly the same way, but this time, see that your degree of freedom 1 is mapped out horizontally, right? So there are two tests here. There is the wedge test and there is the Brown-Forsyth test. I don't want to go into details of the difference between them, but I would say for purpose of this class, if the variances are not equal, just go ahead and report the wedge test. Okay, so assuming the variances are not equal, I will report the wedge test and I will write the evidence at the end. And let me just repeat the evidence section, right? So you will have parentheses F, parentheses open, degree of freedom 1, which is 3 in this case, degree of freedom 2, if we're reporting wedge, is 214.714, parentheses close. This F statistics for wedge is giving us 5.094, and the p-value here is equal to 0.002. Okay, so again, this is not your result. So you report your result in words the way we explained in just the previous slide. After reporting it in words, saying that we rejected the null hypothesis because p-value was smaller than 0.05, and then we conclude that at least one of the group differs from one of the group mean differs from the mean of other groups, right? Then in parentheses you put this numerical evidence to support that statement in word. Okay, so you'll be picking the value to report from the wedge test here only if the quality of variance test is not significant. Only if the equality of variance test is significant. Only if the assumption of equality of variance is not met, right? If that assumption is met, the table you report is this ANOVA table. I'm emphasizing that because it is critical, right? Okay, so that is really that about the ANOVA test. But as we said, this test so far at this point has not given us any information about which group is different from the other group. We know we are comparing 4 groups. We know at this point that one of the group is different from the other groups, but we don't know which one. So we do additional tests. And when you were implementing this, you remember the post hoc test. Okay, but before we talk about that, let's talk about the first size. Assuming we have interpreted the normal ANOVA table and everything is okay, and we find out that, okay, so before I go into that, and then we look at the effect size. The effect size is simply telling us similar thing as R squared told us in regression last class. If you remember how we explained R squared. So the effect size is telling us the percentage of variation in the dependent variable that is explained by the independent variable. So I'm going to write that in words. So the effect size tells us percentage of variation in the dependent variable that is explained by the independent variable. Okay, again, this is a general template. So you want to write this result in the context of the problem. In this problem, the question we are dealing with here, check time. Okay, we need to speed up a little bit. In the questions we are dealing with here, we know that the dependent variable is glucose level. And we know that the independent variable is number of pregnancies. Right, so I'm going to remove the word dependent and independent and put in the actual numbers. I'm going to put in the actual percentage, and I'm going to explain it in the context of the question, and it will be something like this. Let me move this away. I'm going to write it on top here with green. So it will be pregnancies, or not pregnancy, but number explains 6.8%. You're getting that from here. So the first size we are interpreting is the eta squared. Okay. Again, your current version of SPSS might not have the rest of them, but even if it does, we're not interpreting the rest. We are focusing on eta squared. Okay. So the number of pregnancies explain 6.8% of the variation or the variability in glucose level or blood glucose level. And we can be more precise in, yeah, I think that would be okay. Okay, so that is the effect size. That is how that is interpreted. So you interpret it in the context of the problem you're trying to address. Okay. Now let's try to speed up a little bit. Go to the next slide. I'm assuming there's no question here. So you see this interpretation is exactly the same thing as we did R squared last class, right? They are exactly the same interpretation. So eta squared is equivalent to R squared in regression run. Okay, so we are saying so far, all we know is that the one of the group is different from the other groups. We don't know which one. So we need to conduct a post-hoc test. So there are 4 groups here, those with 0 pregnancies, those with 1 pregnancy, those with 2 or 3 pregnancies, right? So you're going to compare each of the pairs. So you'll be trying to compare 0 with 1, 0 with 2, 0 with 3, and find out which one is bigger, or which one is statistically significantly different from the other one, right? And after you've done that, of course, you will need to compare 1 with 2 and compare 1 with 3, right? When you're done with all that, the comparison is not yet complete. 1 pair is missing. Straight. You need to compare 2 with 3. Okay, so these are like 1, 2, 3, 4, 5, 6, or actually 7. Yeah, 6 comparisons that you need to do just to compare, know which one is bigger in 4 groups, or which one is statistically different from the other among the 4 groups. Okay, so I hope that comes out. It's quite straightforward, right? So let's go ahead and look at which one is big, how that test is done using the output for post-hoc. Yeah, so here is your post-hoc test output. The post-hoc test is also called multiple comparison, right? So in your output, you could have seen post-hoc somewhere here, probably, depending on your version, right? But multiple comparison, comparing many sets of pairs, that is something as the post-hoc test, and that's what we're doing. So if you look over here, look carefully, you see that these are in batches, and the one we chose to do is Tukey, okay? If you're interested in this, you take another class, we'll explain the differences between each of those options you had there where you chose Tukey. So the one we're doing is Tukey, and if you look at this, you find out the comparison just was the way I did it on the other slide, right? So first of all, you're comparing 0 with 1, with 2, and with 3. Then you're comparing 1 with 0, 2, and 3. So some of the results are going to be redundant. For example, the result that you got from comparing 0 to 1 will be the same as the result you get from comparing 1 to 0. You just switch the one that came first, right? Okay. But you never had any result that compare 1 to 2 before, and you never had any result that compare 1 to 3, right? So if you come down here again, the results you'll get by comparing, let me use green, the result you get by comparing 0 with 2 will be the same result you will get here by comparing 2 with 0. Okay, but you've never got any result of comparing 2 to 1. You've never got any result comparing 2 to 3 before. So in this column, the result you get by comparing 3 to 0 would be the same thing as the result you get by comparing 0 to 3 here, right? So essentially, you see that the first row is kind of redundant, but the subsequent row gives you some information new. So all you need to do is to follow the pattern I listed here on the previous slide, on whatever test you're comparing. Okay, it's not there. So I'm going to write it again. So we have 4 groups: 0, 1, 2, 3 pregnancies. So these are actually 4 groups. Those who have not been pregnant, and those who had 1, 2, or 3 child, as the case might be. So we compare 0 with 1. So you have 1 test result for this. You compare 0 with 2. You have 1 test result for that, and then you compare 0 with 3. So you are done with that, but you are missing 1 with 2, 1 with 3. When you're done with that, you're still missing 1 more comparison, 2 with 3. So you want to make sure that these 6 sets of comparison are reported in your answer, right? And so it might be 3 sets, it might be 2 sets, it might be 4 sets, it might be 5 sets, it might be any set, depending on how many groups you have. But the goal is to make sure that all pairs are compared, right? Okay, so if we come back to this place, when you're comparing, you're reporting the significant level. So if I look at the significant level here, I found out that this first row, which is comparing 0, I need to clear all that to make it clearer. Okay, that did not go away. Okay, I found out that this first group, which is comparing 0 with 1, that the value, the p-value is 0.04. So it's slightly less than 0.05. So I will say this is significant. So there's a significant difference. If I'm reporting it in my result, I'm going to say there's a significant difference between group 0 and group 1, right? There's a significant difference between those who have not had any pregnancies with those who have had 1 pregnancy. Then you go to the next row. This is 1 with 2. You check the significant level. It is less than 0. I mean, it's less than 0.05. So there is a significant difference between those who have had 0 pregnancies and those who have had 2 pregnancies, right? And then you go to the third group, the p-value is more than 0.05. So this means there is no significant difference between people who have had 0 pregnancies and those who have had 3 pregnancies. There is no significant difference in their blood sugar level. So you must put it in the context of the research you're doing, right? Okay, so, and this is how you go through and make sure that you capture all the comparison depending on the number of groups you're comparing. And so this result is what makes that test complete. It tells you which group is bigger than which. Otherwise, we wouldn't have known otherwise, right? So post hoc test is conducted only when the main test is statistically significant. So if the main test says that none of the group is different from each other, then there's no need looking for those that are different. But if the main test says there is a group that is different, that one of them is different, then you come back here to look at post-hoc test to know which one that is really different. And once you are done with that, this is your mean plot. So this is just a graphical illustration of those average values for each group. So you can tell from here, if you look at group 0 and group 3, if you draw a line from here to this end, I think we're about out of time. If you draw a line from here to this end and a line from this end, you could see that they are not really different from each other. And that's why the result shows that, right? Okay. So you have opportunity to repeat all this in your homework. This is the last slide, I believe. And we've been interpreting the results. You repeat that all in your homework, and we're technically done with new content for this semester. So over here, your answers. If you want to pick them up and look at that, that will help you for your quiz, for your final exam, the quiz 2. And please mark on the attendance before you leave as well. Okay. Oh, you can take one here. Okay. So I hope all this is recorded.